Hello everyone, this is Sunil, and in this video we are going to discuss about some numerical problems on electronic material devices. We'll discuss some questions on crystal structure, and then we'll discuss some questions on Hall effect, then electrical transport behavior in solids, Hall effect, and then finally we'll discuss some questions on semiconductor devices. Okay, so let's see the first questions here. The atomic radius of copper is 0.1278 nanometer. And as we know, copper is a face-centered cubic structure. Okay. That means it has crystal structure of FCC. Now there are three questions we have. What is the crystal lattice constant? Second question, what is the concentration of copper atoms? That means your number density. And third question is here, what is the atomic volume? That means the volume of 1 mole of copper. Now, if you can see here, if taken into consideration of face-centered cubic lattice of copper, so the relation between your lattice constant and R is 2 root 2 A is equal to 4R, where A is your lattice constant and R is your radius. Then what will be my lattice constant here then? 4R by root 2. So as we know, the radius of copper atom is 0.127 nanometer, which is given in the question here. So we can put the value, then we can find the lattice constant, that is 0.361 nanometer. Now the second question is here, what is the concentration of copper atoms? That means your number density. So how can we find out? Now this number density is nothing but N, capital N by capital V. The N is here the number of atoms per unit cell, and V is the volume of unit cell. The volume of unit cell, as you know, AQ. Taken into consideration of your A is your lattice constant. So N by V will be 4 by AQ. Okay. Uh, so and what is AQ then? AQ is your lattice constant. So A we calculated here 0.361 nanometer. So it will be 4.692 into 10 to the power minus 29 meter cube. Then what is the number of atoms per unit cell? As you know, 4, right? So 4 divided by AQ. What is AQ here? 4.692 into 10 to the power minus 29 meter cube. So finally, we'll get uh, 8.52 into 10 to the power 28 atoms per meter cube. That is the answer for the second question. That what is the concentration of copper atom? That is number density. So the concentration is 8.52 into 10 to the 28 atoms per meter cube. Okay. Now, third question is here that what is the atomic volume? That is the volume of 1 mole of copper. 1 mole, as you know, 6.023 into 10 to the power 23. Then what is the atomic volume here? Volume of AQ, that is your A is nothing but your lattice constant, is occupied by 4 copper atoms. Okay. Then the question is here that what is the atomic volume then? The atomic volume is here AQ by 4 into Na. Okay, so Na is nothing but your Avogadro's number, that is 6.023 into 10 to the power 23. A stands for Avogadro. So if you calculate here, so it is somewhere comes to be close to 7.07 into 10 to the power minus 6 meter cube per mole. So this is the answer for the first question. Now let's move on to second question here. This question is based on Hall effect. The question is here, what is the explain Hall effect and calculate drift mobility of electrons in copper given the Hall coefficient and conductivity of copper at room temperature is minus 0.55 into 10 to the power minus 10 meter cube ampere inverse second inverse, and 5.9 into 10 to the power 7 uh, ohm inverse meter inverse respectively. Okay, so in this case actually this is 10 to the power 7 I am writing here. So yes, so the Hole coefficient and the conductivity of copper at room temperature is given. Now we have to find out what is my drift mobility of electrons. Now Hall effect, what is that? Hall effect is applicable to metal as well as semiconductor. Now it is says that when a metal or semiconductor is placed in a transverse magnetic field, then that means a current carrying conductor, if it is placed in a transverse magnetic field, that means your magnetic field is perpendicular to the direction of your current. Then the electric field is generated perpendicular to both current and magnetic field. That is the explanation of Hall effect. Okay. Now, based on that, the question is given here. So let's see how we can solve this question. The Hall coefficient is given already. Conductivity is also given, and there is a relation between your Hall coefficient, charge of electron, and electron concentration, and that is nothing but RH is equal to minus 1 by Qn, where Q is the charge and L is the electron concentration. Now, we also know the relation between conductivity, that means your electrical conductivity, and mobility and charge of electron concentration. That is nothing but conductivity is equal to sigma is equal to Q. Q is the charge, N is the electron concentration, and mu is the drift mobility. Okay. So what will be Q into N? That is sigma by mu d. Okay. Now, if you can substitute this equation here in this equation 1, then what we'll get here? RH here minus 1 into drift mobility divided by conductivity. The question is here is asking here that what is my mobility, drift mobility here. So what is my drift mobility here then? Minus RH into sigma. So RH is the whole coefficient and sigma is your conductivity. So if you can multiply these two things, RH and the sigma is already given. So we'll get mobility is equal to 3.2 into 10 to the power minus 3 meter square per volt second. So this is the solution of second question. Third question is here, the electrical resistivity of a brass disc is 40 nano ohm meter. Okay, that is the electrical resistivity. And the rate of heat flow from a heat source to the heat sink is 15 watt. Now the question is here, calculate the temperature drop across the disk if the diameter and length of the disk is 20 millimeter and 30 millimeter respectively. That means diameter is 20 millimeter and length is 30 millimeter. Now electrical resistivity of brass is given. Rate of heat flow is also given. Diameter is given, length is given. So first we have to calculate the thermal conductivity here. What is the thermal conductivity? Thermal conductivity K is equal to electrical conductivity into the temperature into Lorentz number. The CWFL is nothing but a Lorentz number, and uh, that is a value, and that is a constant value that is coming to be 2.44 into 10 to the power minus 8 watt ohm Kelvin inverse square. Okay. Now this thermal conductivity value we can find out. In this case, at room temperature, so room temperature is 300 Kelvin and electrical conductivity is already given. Electrical resistivity is given, so we can calculate electrical conductivity from electrical conductivity. We can get it from electrical resistivity if we take the reciprocal of electrical resistivity. So we can calculate the electrical conductivity. So here 4 into 10 to the minus 8 ohm meter inverse, that is your electrical conductivity. So So we can get the thermal conductivity, this value 183 watt per meter inverse Kelvin inverse. Then what is my thermal resistance? That is length divided by thermal conductivity into area of cross section. So length and area of cross section already given in the question. So it is coming to be 0.518 uh, Kelvin into watt inverse. Okay. Now question is here, what is the temperature drop? Okay, what is the temperature drop here? The temperature drop is nothing but your what is the uh, that is your 0.518 kilowatt inverse into 15 watt, because this one we get it from here thermal resistance. So this thermal resistance into what is the rate of heat flow. So if you multiply here, that gives rise to your temperature drop here as per the question. So temperature drop here in this question, uh, and the solution we get it here 7.77 Kelvin. So that is a temperature drop. Now let's move on to the next question. An N-type silicon wafer has been doped uniformly with 10 to the power 16 arsenic atoms per centimeter cube. Now calculate the position of Fermi energy with respect to the Fermi energy of intrinsic silicon. Now next, the above N-type silicon, if it is further doped with 2 to the power 17 boron atoms, okay, per centimeter cube, then calculate the position of Fermi energy with respect to Fermi energy of intrinsic silicon. Okay. Now here temperature is given 300 Kelvin, that is a room temperature, and K into T, that is 0.02 minute 59 electron volt. Okay. So how can we do? Now, uh, arsenic gives basically N-type doping. Okay. And what is the donor impurity? It is already given 10 to the power 16. Okay. So 10 to the power 16 per centimeter. Now, basically, this donor concentration is very, very greater than here intrinsic concentration. Because intrinsic concentration of silicon is 1 point into 10 to the power 10 per centimeter cube. So we have in this case, so as donor concentration is very, very greater than your intrinsic concentration, so we can conclude here that your electron concentration is equal to your donor concentration, that is a 10 to the power 16 per centimeter cube, because this is N-type silicon, N-type semiconductor, this one. So that is why your electron concentration is equal to donor concentration. Now for intrinsic silicon, the relation between intrinsic concentration and density of states at conduction band edge is Ni is equal to Nc into e to the power minus Ec minus EFI divided by Kt. Okay, Ec is nothing but conduction band energy, and EFI is the intrinsic Fermi energy, K is the Boltzmann constant, and T is your absolute temperature. Whereas for doped silicon, this is N is equal to Nc into e to the power minus Ec minus EFN divided by Kt. That is nothing but a donor concentration. Now EFI, EFN are the Fermi energy in the intrinsic and N-type silicon. Now if you can divide these two expressions, then we'll get e to the power EFN minus EFI divided by Kt. So that EFN minus EFI will be Kt ln Nd by Ni. Okay, so EFN and EF will take this side. So this one will become ln. So finally we get 0.36 CP. Now this is the first question, that calculate the position of Fermi energy which is Fermi energy of intrinsic silicon. So this is coming to be 0.36 CP. Now if the vapor is doped with boron, that is your trivalent impurity, the accepted concentration is nothing but your 2 into 10 to the power 17 per centimeter cube. Now which is very, very greater than your donor concentration 10 to the 16th per centimeter cube. Now the semiconductor is compensation doped, and compensation converts semiconductor to p-type silicon. So what is my whole concentration here? Na minus Nd. That is your difference of your acceptor concentration and donor concentration. So this gives rise to your whole concentration. Now for intrinsic silicon, this intrinsic carrier concentration will be Nb into e to the power minus EFI minus Eb by Kt. Nb is nothing but your density of state at the valence event H. Whereas for doped silicon, it is whole concentration P is equal to Nb into e to the power minus EFP minus Eb by Kt. That is equal to your Na minus Nd, because this here whole concentration is equal to Na minus Nd, right? So where EFI and EFP are the Fermi energy in the intrinsic and p-type silicon. Now if you can divide these two expressions, whole concentration divided by intrinsic concentration, then it comes to be e to the power minus EFP minus EFI by Kt. So EFP minus EFI will be minus Kt ln P by Ni. So we'll get minus 0.43 EB. So this is the second question's answer, that what is the position of Fermi energy with respect to Fermi energy of intrinsic silicon. So this is the answer, minus 0.43 EB. Now next, move to next question here. That find the resistivity of intrinsic silicon at room temperature. Taken into consideration of intrinsic carrying concentration is 1.5 into 10 to the power 10 electrons per centimeter cube. Electron mobility is given 1300 centimeters square per volt second, and hole mobility is given 500 centimeters square per volt second. So how to find the resistivity? Now resistivity only you can find out when if you can find a electrical conductivity. So resistivity will give you a reciprocal of your electrical conductivity. Now for intrinsic silicon at room temperature, your intrinsic carrier concentration is 1.5 into 10 to the power 10 electrons per centimeter. Mobility of electron is given, mobility of hole is given for silicon. So what is my electrical conductivity here? Ni, that is your intrinsic carrier concentration, multiplied by summation of your mobility of electron and mobility of hole. Now if you can put the value here as per the question, so it is 4.32 into 10 to the power minus 6 ohm centimeter universe. Okay, so that is electrical conductivity. Then what will be my resistivity? Resistivity is nothing but reciprocal of your conductivity. So it is 1 divided by 4.32 into 10 to the minus 6. So it will come to be 231,000 ohm centimeter. So this is the resistivity of intrinsic silicon at room temperature as per the given data. And the next question. Consider a semiconductor with following parameters. Charge of electron is given, as you know, 1.6 in 10 to the power minus 19 coulomb. Electron mobility is given, 1200 centimeters square per volt second. Uh, 1200 centimeters square per volt second. Thermal voltage Kt by Q 26 millivolt, that we know at room temperature. And electron concentration is given 2 into 10 to the power 15 per centimeter cube. Electric field is also given, E 400 volt per centimeter. Spatial gradient of electron, that means your electron concentration gradient. Okay, so it is 2 into 10 to the 20 uh, centimeter to the power minus 3 per centimeter cube. See, electron concentration, as you know, per centimeter cube, but concentration gradient, that means per centimeter. So that is why it is centimeter to the minus 3 per centimeter. Now question is here, find out or calculate the drift current density and diffusion current density of electrons in the semiconductor. So how can we solve? A drift current density, as we know, is nothing but uh, your electrical conductivity into electric field. So all the values are given. So if you can put the value here, this charge of electron 1.6 into 10 to the minus 19 coulomb. Electron concentration is given 2 into 10 to the power 15, which is given 2 into 10 to the 15 here. See, and then mobility of electron is given 1200 and electric field is 400. So finally, this drift current density is 153.6 ampere per centimeter square if you take into CGS unit. If it is SI unit, 1.536 in ampere per meter square. Now next, what is my diffusion current density? This is as per the relation charge into diffusion constant into concentration gradient, right? So dN is nothing but a diffusion constant. Now diffusion constant, how can we find out? So as we know, dN by mu1 is equal to kT by q. So what is dN? It's mu1 kT by q. So if you can put the value, you can find the value of dN. Now this dN value, you put it here in this equation, and finally you will get the diffusion current density is equal to 998.4 ampere per centimeter square, which is a CGS unit. And if you convert into SI unit, then it is comes to be 9.984 ampere per meter square. So these are the some questions which we have solved as per the numerical problems in electronic and materials and devices. So I hope this solution helps you. If you have any comment or any queries, please you can ask in the comment box. And if you have any other doubts, you can ask at any time. Okay. I hope this video finds you informative content, and it gives you a lot of details about how we can solve any particular question as far as electronic material and devices are concerned. So I hope this lecture video helps you in many ways. So with this, I would like to conclude this session. Thank you, everyone.